Okay, so this is, I've chosen this title. I have not given titles for the talks. Speakers choose on their own. I just given what to talk about. So this is computational gas dynamics. And this is not fluid dynamics or fluid mechanics or something like that. And the reason is gas is very compressible. And a lot of fluids is incompressible fluids, classic fluids like water and so on in the lab. We always deal with incompressible fluids. So that's why gas dynamics is important. In astrophysics, the compressibility is extremely important. Shock waves, supernovae, AGN jets, all these involve extreme compression. Okay. So this is like a very broad overview of what we are going to talk about. So what we'll sort of in this workshop and the course that we are dealing with, we'll be talking about Euler, Navier-Stokes, MHD, the equations. These are continuum equations. That is, you have like averaged over particulate nature of gas molecules. Right? So these are continuum equations, which are very good for dense gases, but also surprisingly good for seemingly collisionless plasmas like the solar wind, because magnetic fields make even a formally collisionless gas or a plasma quite collisional in a lot of respects. So, these equations describe systems ranging from accretion onto compact objects to the evolution of the universe as a whole, like galaxy formation in cosmological context. You're solving basically hydrodynamics in presence of dark matter, gravitational dynamics. So these equations, Euler equations, have been studied for centuries by physicists, engineers, mathematicians. And over past few decades, numerical simulations have become extremely important because fast computers have become available. So we can do these numerical experiments and build our intuition and make predictions for example, the drag experienced by an airplane or the lift generated for a particular wing design. The problem without computers is that the analytic solutions are extremely limited. You can do linear analysis, study waves and instabilities, but that's just linear physics. You can do some nonlinear things like Bondi-Parker solution, blast waves, self-similar solutions. So you can do a little bit of phenomenology of turbulence. There's a cascade and stuff like that, but that's about it. There isn't a lot that you can do analytically in the nonlinear regime. So numerical simulations come in here that for various situations, you can actually solve these first equations regime. And you try to understand things quantitatively first, and then quantitatively. I think teams, if people are joining online can mute themselves, that will be good. Thanks. Okay, so like for example, qualitatively, in astrophysics, we're studying things which are so far away from us, and a lot of times you don't even know like basic physical phenomena going on in a particular system, right? So you have to understand things qualitatively first. Quantitatively is, for example, space weather or weather prediction on Earth. We know physics, we know a lot of phenomena that are important, but the aim there is to predict whether it will rain tomorrow or not, right? So this is quantitative prediction. So let's start from the basics. So Euler equations are partial differential equations. So partial differential equations have independent variables. Here, say time and x. The boldface is vector. And then the depends on the aim is to find the density, velocity, bulk velocity, and pressure as a function of space and time, given the initial and boundary conditions. Okay. So this is what we are trying to do. Now these are the equations. These are based on physics. So this is basically conservation of mass, the first equation. The rate of change of mass density rho depends on local divergence of the velocity field. So if you have this fluid element and there is some flow field around it, you calculate the divergence of that flow field. And that is what is going to tell us how the density of this fluid element will change as you move along that fluid element. So this is something called a Lagrangian derivative. This capital B by dt is a Lagrangian derivative, and this is the definition of a Lagrangian derivative, right? So you have some quantity f, a field f. You're looking at how f changes as you follow the fluid element. So this is basically the definition. So limit delta t going to 0, stated at its new position and at the new time, minus original f divided by delta t. Okay? So now there are two variations. One is variation in x and variation in time. You just sort of do some manipulations. What you get is this first limit, which is just a partial derivative of x. And then you have this, the second. Right, so this is so the order is interchanged. So the first difference is this one, u dot grad f. Because like how much does f change with time is the gradient of f. And the first term here is partial f and partial t. Okay, so this is the Lagrangian derivative. All these are Lagrangian derivatives. So the second equation is basically equation of motion, Newton's law, f equals ma. So this is rate of change of velocity, which is acceleration of a fluid element, and these are the forces acting on the fluid. There are surface forces, pressure forces are surface forces, and there are body forces like gravity, which act in the bulk. And so this is mass conservation equation of motion, and the third thing is energy equation. So this is the Lagrangian derivative of total. The internal energy density is given by compression, del dot u. Okay, so these are basic equations that you need to solve. You can write these equations in various forms, and it's useful to know all the standard forms of these equations, because different forms provide different insights. Okay, so this Lagrangian form is actually used in something called smooth part hydrodynamics, or HPH. This was very popular in galaxy formation simulations. When you treat gas or fluid elements as particles. But you see, there are these forces for which on the terms of the right hand side, where you have to calculate gradients and divergences. So how do you calculate these things on the right hand side, like gradients and divergences? For that, you need to do something called extrapolation. You have to actually use the different particle or fluid element properties and calculate a local gradient. So this is what this kernel approach is in SPH. So this equation can also be written as this. The energy equation can also be written in this entropy form. Okay. Now those were the equations. Now, how do you solve these equations? And there are various approaches. Euler equations, the way I presented them, were just basically conservation laws. Okay, conservation, mass, momentum, energy. But you can also derive them from the fundamental equation, like Boltzmann equation, which knows about particles. If you take moments of the Boltzmann equation, you can get the same equations. If you assume that the distribution function is Maxwell-Boltzmann, which is a very good assumption for collisional gases. Okay, so these are, again, to recall, these are partial differential equations. Independent variables are time and x, and the dependent variables are given here. As you can see, there are 1 plus 3, 4, plus 1, 5, plus 1, 6 unknowns, but only 5 equations. Mass, scalar equation, velocity, vector equation 3, and the fifth one is the energy equation. Only 5 equations, but 6 unknowns, so you need something else. And this is what that something else is. This is the ideal gas law. P equals gamma minus 1 E. This is valid for dilute gases and plasmas. Okay. And if you are working on neutron star matter, you'll have some more complicated equations still. So this ideal gas approximation holds. Okay, the size of the molecules or the size of the particles is tiny compared to the distance, distance between these molecules. And this is true even for plasma. This is also a good equation of state purpose, at least in this fluid limit. Now, the purpose is, as I mentioned, you have to solve these partial differential equations of PDEs. So they're given in initial conditions. Conditions are specified at the boundaries, and you have to start from here and march in future. So these are space-time diagrams. So start getting familiar with this because you'll see a lot of them very shortly. So this is space, this is time. And this is used a lot in special relativity, but this concept is independent of that. So space-time, initial conditions, how do you evolve in time? So in proof of context, the initial conditions are defined and are specified in init.c and in boundary.c, essentially. So to numerically solve these equations, you need a grid or a mesh, and you have to discretize these partial differential equations and march in time. So here, actually, it does not come out nicely. Here, I've shown that the same equations are actually solved if you're interested in flow around airplanes. What is not seen properly is that there's an unstructured mesh around this, right? You want a lot of resolution near where there is a lot of action, like the wings of the airplane. There is boundary layer, boundary layer separation and stuff like that. So in aerospace applications, a lot of creativity goes in creating such grids, and that's a field in its own. How do you create these grids, and how do you numerically sort of take care of it? We are not going to talk about that here, because in astrophysics, we know so less. We want to understand things qualitatively, right? So our boundary conditions are simple, and meshes are also reasonably, we use structured meshes. Okay, so this is another form of Euler equations, the conservative form, right? This looks different. Previously, we had this capital B by dt. Now we have this partial by partial d of something plus divergence of something is equal to 0. This is what is known as the conservative form. So this is conservation of mass, momentum, and total energy. Some of you have seen these equations, some may not have. Yes?
If you make it gaseous,
here, we are assuming gas is electrically neutral, but we will actually come to MHD tomorrow. Then we'll relax that assumption. But a lot of these things actually carry over. In MHD approximation, you have additional terms. Yes, here we are assuming that it is neutral gas. But a lot of times you actually see that even this equations are applied for ionized plasmas to get a first answer. Okay. So this is actually very important form. The form is like this, right? Partial by partial d of capital U. So U is a vector. F is a vector flux. So partial by partial d of U plus divergence of F is equal to 0. If you take a volume integral of this, like this, you get the rate of change of volume integrated U is equal to dV times del dot F. But we know Gauss's law. You can convert divergence into an area surface integral, which is what this is. So this is the integral form of these equations. Okay, the rate of change of conserved quantity is equal to integral of flux over all enclosing surfaces. This is what its interpretation is. It is also called the integral or the weak form of these equations. Okay, weak form in the differential form of these equations break down at discontinuity, and these solutions admit discontinuities. You have shocks, so you cannot take a derivative at the shock because it's a step function. So, but this integral equations all conservation laws are still valid. Okay, so that's why this D form is extremely useful because it applies even at this function. Yes, capital I. What is capital I? So this equation is a vector equation. So this is divergence of a tensor. So this is UU tensor. I is the identity tensor, delta ij, right? You could have also written as minus grad phi, right? But since I'm writing it in a as an explicit flux conservative. Okay, so this is Euler equations. What is its connection with Navier-Stokes equation? Another equation which we are all familiar with is they are extremely related. So these are the Navier-Stokes equations. This is basically equation of motion, Newton's laws, the viscous fluid. So you have an explicit viscosity term on the right hand side. In Euler equations, I did not put the viscous term, but it doesn't mean that viscosity is not important. It's an extremely important thing. It's just that we are not explicitly modeling it. In a lot of astrophysical scenarios, the Reynolds number is huge. So we are really not looking at viscous phenomena. But viscosity is important because viscosity leads to irreversibility. So these are Navier-Stokes equations. This is equation of motion. The mass conservation equation becomes divergence of u equal to 0. Okay, so there is no evolution equation for density. Okay, density is constant. For example, for water or for normal applications, this is a very good approximation. Now, what about the pressure? Pressure is an unknown here. You don't have a separate equation for pressure like the first law of thermodynamics. What you do is take a divergence of this equation and use divergence of u is equal to 0. So you get a Poisson equation for pressure. This is that equation. Okay, so this is a Poisson equation, just like del squared phi equals 4 pi 0. You know, the gravitational dynamics, the equation of gravitational dynamics, or even the same equation. And this symbol grad u, double dot grad u, is nothing but you take grad u and you dot itself with itself so as to create a scalar. So this is partial I uj, partial j ui. So this is Einstein's summation. So I and j go over 1, 2, 3, and it's summed over. So these look quite different from implicit Euler equations, and these are applicable in the limit where Mach number is small, or infinite sound speed limit. Basically, in these systems in this system of equations, you do something here, the whole medium knows what happened here. Right? There is instantaneous propagation of information because speed of sound is infinite. So right, this is the form that you can write. There's the bottom equation is the form that you can write by doing a de-dimensionalization of these equations, and there's one by Reynolds number. Right. Wow. So here is a comparison of the two. I've just sort of written them again. Here you have just 3 evolution equations for velocities, but there are 2 constraint equations. Divergence of u is equal to 0 should be respected at all times. And this should be respected at all times. Poisson equation should be satisfied at all times. But you are only evolving u. Here you're evolving all these unknowns. Here we don't have explicit viscosity. Yes.
But don't you wait for the Poisson equation for pressure equivalent, or you have to satisfy them?
They have to be satisfied independently because you have to solve for p in order to evolve this equation. Right? So if you take divergence of this equation, you get this equation. Right? So the third equation, the Poisson equation for pressure, comes about by combining this and that. Right?
So we also have the equation of state too.
Here, there is no equation of state. In Navier-Stokes, there is no equation of state because everything is overwhelmed by the fact that information propagates instantaneously. If you want
Size of the system is quite, we can consider that it has small size of the system.
that's right. Or you can think in terms of velocities being small, sound speed being hard. All those are equal. Now, here I've not put in explicit viscosity, but don't let that fool you saying that it's a reversible system. There is an additional constraint, that is the Lagrangian derivative of entropy is greater than or equal to 0. Where entropy or specific entropy is entropy per unit mass, is defined like this. So this has to be respected, and this is respected if you have viscosity. Even if viscosity tends to 0, it's extremely important. Okay. Right. So this approach, and most of the astrophysical codes use this approach because compressibility is important, and we want an explicit viscosity. This is actually in the fluid dynamics language called a large eddy simulation. Okay, and this particular approach is actually called an implicit large eddy simulation because you're not doing an explicit model for subgrid turbulence. Okay. The right hand side is something, is the approach taken on the right hand side is called a direct numerical simulation, where we are resolving the viscous phenomena. And the most powerful methods for solving Navier-Stokes in simple periodic boundary conditions are the pseudo-spectral or Fourier methods. You have periodic boundary conditions, you can solve this in Fourier, some terms of it in Fourier space. Actually, this u dot grad u is not solved in Fourier space because it leads to convolution, and that's an expensive thing to do in Fourier space. So that's why it's pseudo-spectral. Rest of the terms are done in the K space, whereas this term, you do it in the real space, but making sure you're doing everything consistent. Okay. So yeah, feel free to stop me if you have any questions. But I did really want to start with extreme basic things so that we are all on the same page regarding what we are actually doing. So in this whole tutorial on solving all the equations numerically, this vector form is extremely useful. Knowledge of multivariate calculus and linear algebra will come handy. So let's see on that. Okay, so this is the same Euler equations written in a matrix form. Okay, so you have this velocity vector. It's a column vector of three velocities, u, v, and w, or ux, uy, and uz. So this is the conservative vector, right? Capital U. This is mass density, momentum density in x direction, momentum density in y direction, momentum density in z direction. E is the total energy density, which is equal to the kinetic energy density half rho u squared plus internal energy density P by gamma minus 1, where we have used the equation of state. Okay. Now this H is flux. So the other thing is I have actually taken material from different books, which I'll acknowledge at the end. So my notation is not fully consistent, right? But I'm hoping that you have learned enough in these lectures that you will figure that out. So this is the H. Okay. Now H, this is the matrix form. And you have 1, 2, 3, 4, 5 columns and 3 rows. So you can actually see partial by partial t of rho is equal to partial by partial x of rho u plus partial by partial y of rho v plus partial by partial z of rho w. So basically, this is how you combine this del dot operator with this matrix H, right? So you look at this, these are 5 rows of this column vector. And if you compress each of these, you actually get, there should be a transpose here. That's a column vector. And this, if you do the matrix thing, you'll get a row. But if you just put a transpose, you'll get this equation. So, get used to seeing equations in this form. The content is the same. Now, Euler equations have 1 plus 3 plus 2, 5 unknowns. There are 1D, there are 3 unknowns, right? Rho, U, and internal energy density of pressure. It's, you want to start simpler, okay? And that's why there are a lot of these model equations that people use to build their numerical schemes, okay? So I've listed some of them here. So again, the first equation there, ut plus fux is equal to 0, is a set of hyperbolic equations. We'll actually come to what hyperbolic is in a bit. So this is the set of equations. These are conservative equations. F, U, X means that it's partial F or partial X. It's the same form. I have not written this underscore X as now by now X. Okay? And this is 1D, so I'm not dealing with Y and Z direction. So it's the simplest PDE in 1D. Okay, so this now F by now X, and in the cases, the flux is a function of U itself. Like in Euler equation, F, the flux, is rho U squared plus P, and the third is energy. It's also a function of the unknown. So a lot of times it's a function of U itself. So now F, now X is now F, now U. W now X. This is just chain rule for this is multivariate calculus. And this now F, now U. F is a vector, U is a vector, now F, now U is a different, right? Which is a lot of times called A. Okay, and this A is a function of U itself, and then there is UX. So be familiar with this notation. Now, the hyperbolic equations, or the equations of this form, eigenvalues of A are real. That's the definition of hyperbolic equations. These are some of the examples of hyperbolic equation. So if this vector U is rho and rho U, and flux is rho U plus rho U and rho U squared plus P. This is just the first equation is just conservation of mass. The second equation is momentum equation. There is no third equation for inertia because we are assuming a polytropic equation of state. So, for example, this one. So this is simpler. There are only 2 unknowns. So this is also used in some cases. These are isentropic equations. Sometimes people use isothermal limit gamma equals 1. That's isothermal. The nodal codes provide you with the option of solving equations with the isothermal limit. Now, even simpler than this is just one dependent variable. So examples of these of just one dependent variable or scalar equations. So these are scalar equations. The first set of equations was a vector equation because there were 2. Here we have just one dependent variable, like 2 independent variables. So ut plus ux equal to 0. The first equation there is something called Verger's equation. Okay, and you can write it in the conservative form trivially like this. This is a nonlinear equation, right? You can see this term is u squared. It's not lambda times u. It's u squared, so it's nonlinear equation. The second equation, or the direction equation, or the linear direction equation, or also known as one-way wave equation, is given here, where a is a constant. This is a linear equation. These 2 equations are building blocks of finite volume methods. Right? A lot of, initial work that sort of gave a lot of breakthroughs in our ability to solve Euler equations came through by looking at these simpler equations. Now, this equation is almost trivial, right? The convection equation. We know its solution analytically, okay? And the solution is just that the initial waveform, right, just propagates, maintaining its form by a constant velocity a. So that's what this mathematics says. We'll actually come to this in a bit. So now, what about the definition of these? What is hyperbolic, and so on? So it's just a classification of partial differential equations. So this is not exhaustive. Like, if you go to mathematics books, there are like chapters of when do you call a set of PDEs hyperbolic, parabolic, or elliptic. But the purpose here is not that. We're just giving you prototype equations which we encounter in physics a lot. And classifying these into these different classes and just tell about the qualitative content. Okay. So for example, there are these examples that I've given. So, essentially they are classified into three classes: hyperbolic, parabolic, and elliptic. Okay. Hyperbolic equations describe wave propagation at finite speeds. So hyperbolic equations, almost everything in physics has to be described ultimately by a hyperbolic equation, right? Because the speed of light is finite. Nothing can travel faster than the speed of light. So there has to be information lag if you go far away. So these are really fundamental. This is a way, the first equation, this is a way in which you have encountered wave equation when you solve like sound waves or waves in ENM. This is the form that you encounter. This is a second order partial differential equation, but it can be decomposed to two first order partial differential equations. These are linear equations. The way I have written them, they're linear. All three of them are linear equations. So this actually, if you recall your courses, the solution of the first equation can actually be written as a linear sum of waves propagating in the opposite direction, right? Fx plus Ct and Fx minus Ct, and G x minus Ct being not the same function. So this is the first equation. The second equation here, the parabolic equation, it sort of describes diffusive transport. Okay, the thermal diffusion equation is described by this. And viscosity, resistivity, all these del squared terms which appear on the right hand side are parabolic terms. So both of these are sort of modeled as initial value problems. So you have at t equal to 0, you have that you have put on a flame, and you have the other end touching your hand. You are given initial conditions, you're solving how would it evolve later on. This is and similarly, these are also initial value problems. Both of these are initial value problems, but very different in character. For parabolic problems, information travels, even if for hyperbolic problems or sound waves, if someone is beyond the sound horizon, they have zero idea of what's coming. In parabolic equations, that's not the case. Even though you only feel the main diffusive transport over a diffusive landscape, the impact of diffusion is perceptible, very little though, even at very large distances. Now, the third class of equations here are also extremely common. Maybe I'll ask that. Where have you encountered equations of this kind? Electrostatics, magnetostatics, steady state of this equation is sort of the equation. Yes. So these are also extremely common. Like in astrophysicists, people who deal with gravity, del squared phi equals rho by geo. Our favorite equation is also this form. Right hand side is 0 here, but if it is non-zero, there essentially is not any difference. The nature of the equation is determined by this. Okay. So since the nature of solutions are different, the techniques to solve them numerically are also different.
Yes.
Oh, very nice. Okay, so spooky action of the distance. I don't know. And who has not heard of this earlier? You have not. Physics people must have heard of this spooky action at distance. So, people when Newton and so on discovered gravity, they all in Laplace's time, they knew that del squared pi equals 4 pi g rho. So what if you change your mass somewhere very far away, its effect is felt instantaneously, right? That's the nature of these equations of 2. So that's why this is a spooky action at a distance, right? You are causally disconnected, and yet you are able to affect the gravitational field far away. So this is just an approximation. This cannot be the fundamental equation. Okay, this is what spooky action at distance is. That's right. That's right. That is correct. But that's a little more, I like down to earth things more. And I actually don't understand those things that well. So let's get back to hyperbolic equations.
So there is cosine like L2.
That's where phi
Del square pi equals 4 pi d rho. So if you just remove one of the mass, the effect will take some time to forget at the speed of light.
That's right. So that's right. So that's why the correct equation is Einstein's equation, which actually incorporates the physics. Right? Newton's equations are just an approximation. Okay. So now let's get back to let's get back to the hyperbolic equations that we started with. So we solved hyperbolic equations. So this is a scalar. So when I say a scalar equation, there's one dependent variable. This is the scalar equation. U is just not written in bold. So this is just this is a form which is dou t plus. So the conservative is dou f dou x. So dou u dou t plus dou f dou x equals 0. But what I've not assumed, or not even assumed here, is here I've not assumed that f is a function of u only. In fact, I've assumed that this velocity a can actually be a function of x and t. That's not the case for Euler equations, other equations. But in general, this is also fine. Okay, so this is a 1D scalar hyperbolic equation in primitive or characteristic form. This form of the equation is called the primitive form. Okay, because it's like dou t plus u dot grad, right? Not as divergence or something. So that's the conservative form. Now, what it says is that this quantity a here has a dimension of speed, velocity. So dx by dt, if you choose dx by dt is equal to a, so these are space-time diagrams, so xt. So if you go along paths, which is described by this equation, dx by dt equals a, these curves are called characteristic curves of this equation. Okay. So here on the right, I have just illustrated these characteristic curves. So what you do is, so this is a space-time diagram at t equal to 0. You know what u looks like at all x's, essentially. So now you just follow these trajectories and just ask. So if dx by dt is equal to a, if you're going along the characteristics, what does it mean for this equation, the first equation? What it means is the change in u if you go along the characteristics of 0. Because that's just the total derivative of u moving along the characteristics. And mathematics is shown here, you can actually verify it. So you go along these characteristics, u is constant. So what it suggests us is that if you want to know, for example, what the value of u is at this point, this blue point here, what you have to do is just go back. You should basically retrace the characteristic and go to t equal to 0. Whatever the value is here will be the value of u at this point. So if you know the characteristic, it's extremely trivial to solve the partial differential, this hyperbolic equation. So you can so basically with this way, you can map every point to the initial or the boundary condition, both of which you know, but not so fast, Watson, as Scheller could say, because in these nonlinear hyperbolic equations, these characteristic curves do not remain separated. They can converge, they can diverge, and you cannot do this mapping. An example is shown here qualitatively in the bottom. So here, if there are these two characteristics on which the value of the dependent variable is u1 and u2, and if they merge, what will be the value of this common characteristic that emerges? Right. So also, and this is, well, formally it's fine, but it does not really work in practice. The other thing that we have to keep in mind is the differential forms of the equations apply everywhere, except at shocks where we have to invoke the integral or the weak form. Let's move on. So here is the invection equation. Here is some initial condition, can be discontinuous, but it should, it should be a function. You cannot have two values at a given x. That's not a function. That's, you cannot have two values of density at a given point. So it's a physical quantity. So it can have discontinuities, but it's a, it's a function. So the solution of this is just this same form just moved by velocity times time. Now you can actually show it analytically that the solution ux comma t is whatever the u is at t equal to 0, but x replaced by x minus at. You can formally do it. You take dou u dou t. Now u is only a function of x minus at. So you do the u not the psi, where psi is just x minus at, and the partial psi by partial t is just minus a. And you can actually just see that dou u dou t plus a dou u dou x will identically give you 0. Okay, this is the mathematical way of showing it, but it's also obvious if you think physically. These are the characteristics of this equation. If the velocity is greater than 0, characteristic means that if you go along those paths, the value of u should not change. And this is what exactly it means, that if my condition is something like here, if I go with go a distance at, the value of u should be the same. This is just another way of saying the same thing.
We just plot the value of this equation from the plot.
What
in the y direction?
Y direction?
Right.
This is y axis. This is the value of u t equal to 0. So u naught is the value of u at t equal to 0. And this is like u. This is like a function of two variables, and this sort of nicely writing it as a function of one variable, because derivatives are much nicer than partial derivatives. Okay. Now this is Berger's equation. This was the invection equation trivial actually. Berger's equation is shown here: partial u by partial t plus ln of x of u squared by 2 equal to 0. This sine wave is the initial condition. Okay, how does this evolve? So basically, we know the recipe. Just if you're interested in finding the value anywhere at x comma t, you go along the characteristics and map it to what's the value at t equal to 0. So for example, if this x and t, I want to know the value, this is the characteristic, and I map it here, and that's the value. So what it means physically is that if you have this wave, these portions of the wave are traveling with velocity 1. Okay, these portions are traveling with -1. And there was something here, we're traveling with half. So, but you can actually easily see here that eventually, if you evolve it much, so this first one is like fine, but if you evolve it further in time, it can cross itself. You can have 3 values at the same location, which is not allowed, because Euler equation, we are not writing viscosity explicitly, but it will kick in at some point when the gradient becomes huge. Okay. So that won't allow this solution to be physical. What will happen instead is this: the viscosity becomes important at this, boundary there. That's the shock. That's right. And here are the characteristics drawn. So what you do is you just say that, let's say start here. So dx dt is equal to u, and u is constant around that. So you basically take the value of u here and just move it at that velocity, and you know when it will cross. So in fact, I shared the code for this. In fact, whatever these convert things, whatever I am showing, I have shared the code with the Jupyter notebooks for you to check out. Okay. So weak solution in the shock jump. Okay. The Euler and Berger's equation, even if you start with initial smooth initial conditions, can lead to shocks, which are discontinuities. So you have to deal with shocks and discontinuities. So as I mentioned earlier, the integral form is more fundamental and corresponds to a weak solution of this equation. You know, weak solution is can be formally defined in mathematics. We'll not go into that. But we have some participants from TIFI camp who are sort of champions of research off with that. Okay, so yeah, so these are, you've already seen this. Now look at this equation. So this is the the same equation, our scalar hyperbolic equation in one dimension. So what you do is you integrate it in space and time. So this is the space-time graph. You are at this x and t, and what you do is you create this little control volume. This kind of analysis is called control volume analysis in engineering. So you make this little volume, you integrate it over this x and this time, this equation. Okay, so what is partial over partial t? When you integrate it over time, it's the value of final time minus initial time at the same position. So value at final time is, so there's a jump. Okay, so this is the shock or the discontinuity that we are anticipating. So if you look at the final time, the value there is UL. So just on the left of this discontinuity, the value is UL, left. L is left, R is right. So the value, so the same value actually remains on the left and right, even in time. We're just going for a little time. So this is delta x times UL minus UR. That's delta. So again, if you do the same thing here, so it will be F evaluated at right minus F evaluated at left. This is right, this is left. This is at t, and this is t plus delta t. Okay, so this is what you get. And now this dx by dt, delta x by delta t, is the speed at which this front will move. Okay, so if you just sort of manipulate it and just identify the shock speed, capital S, with this delta x by delta t, that's just this, which is nothing but the ratio of change in flux across this discontinuity divided by the change in conservative variable across this discontinuity. So this is basically the shock speed, and this is called Rankine-Hugoniot jump condition or shock jump condition. A shock is basically very sharp jump in conditions. Okay. If you have if you deposit a lot of energy instantaneously in a very small volume, it will launch shocks. If you change conditions extremely fast, you can launch shocks. But this continues to be new. So, as I said, these characteristics are merging in this previous example. There is UL there and UR here. What do you, at what speed? So you will have a discontinuity that we know. Just on the left is UL, just on the right is UR. How does it evolve in time? For that, we are anticipating that there will be something like a shock, and it will propagate with the speed. And we are calculating the speed in terms of these conditions just to the left of the shock and to the right. This is that. Now, if there is no jump here, right? If this is a smooth function, this is just a partial derivative, basically derivative of f relative to u. So basically, s equals au. That means that if you're smooth smooth dependent variable, it will just move at the characteristic speed, which we already saw. So this just generalizes it to this discontinuous case. This is the shock speed. It's actually extremely important to know. Okay, so these are shocks. These were shocks. Now, what about shocks? Are not the only nonlinear waves. We also have something called rarefactions. Okay, now consider our favorite Burger's equation. So Burger's equation has nonlinearity in it. His Extraction equation does not. So if you have to understand nonlinear phenomena, you have to deal with Burger's. Okay. Now, so this is your initial condition. On the right, value of velocity is 1. On the left, value of velocity is 0. Now, how does it evolve? In fact, there are many weak solutions for this problem. This one, where you have a shock, is a weak solution because on the right, characteristics are moving with 1. On the left, characteristics are not. They have a velocity 0, and there is a discontinuity. Okay, so this is a shock solution. It's a weak solution, but it's not the physical solution. The physical solution is this solution, which is this slanted straight line. This is called a rarefaction wave. Okay, and the reason that this is the correct solution in this case is if you sort of say that it does not have an infinite slope but a slight slant, you will see that all the characteristics actually have a tendency to stretch out. If you just instead of making it a step, you just sort of make it very large slope. You can then you use the fact that things are moving at the local characteristic speed. They just stretch out. So this weak solution is an unstable solution. So here are the space-time diagrams of old friends. So this is the puzzle that was presented at the beginning. On the left, characteristic speed is 0. On the right, characteristic speed is 1. Now, what happens here? Basically, this is, in other words, what is the nature of solution in this space-time regions? Now, this is the shock scenario. Right? So what you have is in the shock, you have the value which is at left, which is 0, and beyond the shock, the value is 1. Okay? This is the shock scenario, which is the unphysical scenario. And you can actually see for Höringer's equation, the shock velocity is just the same formula, Fr minus Fl divided by Ur minus Un. F is U squared by 2 for Höringer's. So Ur squared minus Ul squared divided by Ur minus Ul. That's just Ur plus Ul by 2. So this is a line of slope between the slope, average of slope here and here. That's the shock scenario. This is what the real thing is. This is the rarefaction fan. And it's called a fan because it looks like those old-fashioned fans that we used to have. I don't know if you guys have seen those. Okay, and this is the mathematical solution of this rarefaction. Any questions? Yes.
So it looks like the rarefaction is more physical than the shock. From physical.
More physical than a shock in this particular situation, yes. Not in all situations. If the situation was reversed, if you had 1 on the left and 0 on the right, the shock was the right answer. Even from the physical perspective, if the characteristics are running into each other, you will have shocks, right? See here, the characteristics have a tendency to run into each other. This is what will give you a shock. On the other hand, for a rarefaction, here you have a rarefaction here. There's a rarefaction wave here. You see here, the characteristics are moving away from each other.
It's like one is stable, the other is unstable.
So we will actually have, in the hands-on session, we'll do a Riemann problem, the sound shock problem. And there we will see any general discontinuity breaks into these things. This is not the end of it. We'll encounter this quite a bit today.
Shocks are also physical in the sense that, astronomers calculate their temperatures and all for Shashank solutions and everything. So they're very real. We observe.
Yeah, so if a lot of shock stuff was bomb research. So we know they are very real. We don't even have to look at remotely, we can actually see. Whether there's this terrible accident recently of the submarine which went for, basically, the same thing, just collapse, shocks, explosion. Okay. Now, you've learned all this, what I've told, but why do we care about this? This is supposed to be a workshop on numerical methods, right? So you guys can wake up. The numerical methods are intimately tied to the physical phenomena that we're studying. They're not two different things. So here is what I'll actually tell you a little bit about why we have to bother about what we did just before this. The integral form or the conservative form of these equations motivates the finite volume approach of solving hyperbolic conservative equations. Okay, so this, again, is scalar conservation law. If we integrate it for this control volume, now this is a control volume in a discretized grid in X and T. Okay, so this is a domain. So you're solving equations on a grid. You have a domain in X, and you're studying time. So you have a grid essentially in time as well. So what you're doing is using this equation in this control volume. We have actually seen this analytically just like 2 slides ago. Here we are doing the same thing. So now when you integrate it over, so let me get the indexing right. So xi is the center of the spatial grid. Xi minus a half is half off-centered on the left. Xi plus a half is half off-centered on the right. Similarly, Tn is the time now, and Tn plus 1 is the time in the next step. So if we do the same manipulation, so the integral on time will get integral over un plus 1 minus un. The dx remains. Similarly, the flux term, the x guy gets integrated over, and f values at the boundaries at I plus a half and I minus a half remain, and you have an integral in time. This is equal to 0. Now, the finite volume approach, which Dipanjan is going to talk more about later, basically deals with these volume average quantities, capital UIN, which is 1 by delta x integral of u over x. This is just the first term times delta x, right? Similarly, you'll have capital UI n plus 1 minus capital UI n times delta x. If you just do this. On the right-hand side, what we have is time integral of the flux over I minus a half phase. Here, this is I minus a half phase. This is the integral of flux entering into the domain from Tn to Tn plus 1. Yes. Now, if you look at this equation, and if you substitute these things here, so you get u capital Ui n plus 1 is equal to capital Ui n minus n. Basically, you get this form of your evolution equations. How does u change in the next time step given the present time step? It changes because of the fluxes leaving and entering the box. Very nice physical analogy, right? I told you these are conservative forms. Whatever the change in the volume is because of fluxes leaving through the surface. The numerical scheme is built on that principle. Okay, so that's why this is very successful, because it builds into this fundamental thing that must be respected. Now, if you average this equation over the whole domain, basically I equal to 0 to n minus 1, what you'll see is that f 3 by 2 appears in grid cell 1 and grid cell 2. So here it appears with the positive sign. On the left grid, on the right grid, it appears with the negative sign. So all the internal fluxes just get cancelled. The sum of ui n plus 1 is equal to sum of ui. So basically, I'm just adding up this equation over the whole domain. It's just basically what this says is that the volume average u only changes because of the boundary fluxes. All these internal fluxes are cancelled. But the problem, the whole novelty now lies in calculating this f I plus a half n plus a half or I minus a half n plus half. Okay, because we don't know the solution at these intermediate times. Godunov method, which is a term you must have heard already and many, many times, it assumes that the initial conditions are piecewise constant. And then you have the initial condition is jump at x I minus a half and I plus a half. Those problems can actually be solved analytically. Okay? In that case, you can calculate this flux exactly. So you have assumed that the solution within the zone is constant. Right? That's not, you really want to have linear and higher order approximations, but we don't know the analytic solution for that. So this is what the Godunov approach is. You saw this discontinuity problem. So at t equal to 0, you have a discontinuity, and you want to see how this propagates in time. Smooth, constant discontinuity, and you can solve it in time. Yeah, this initial condition where you have a discontinuity at t equal to 0 is called the Riemann problem. This is a very special initial condition for Euler equations as well that can actually be solved analytically. If you have a general variation, it cannot be solved analytically. So that's why this Godunov method is so popular, because you have piecewise constant. When you solve the Riemann problem and when you get the flux, once you know you get flux, you integrate this out easily.
Is it not can also be not piecewise, but what's your
That's right, but that's not Godunov. That's like a higher, they're not solved that analytically. Those require some other diametrically. No. Tricks? No. Facts. Okay. One. So in the last few minutes, I want to just still now we were dealing with burger, advection, and so on, but really want to deal with the real monster, which is the Euler equations. What is sort of the philosophy of dealing with Euler equations? And the 1 minute is going to talk about this. Is you start with the set of hyperbolic conservation laws, like Euler equations. You can write it in both conservative and primitive forms. You can actually transform them into a form which is a diagonal or a characteristic form. And this is where we want to go. Basically, you can break down these three unknowns into simple waves, which you can actually solve for. And this is the diagonal or the characteristic form. Now, this mathematics looks quite ugly, but it's actually very easy to do. This is that A Jacobian. You have a 3 by 3 Jacobian for Euler equations. You can actually work it out. And I'd encourage you to work this out. So that's why I've written HW derived this. This is the homework problem. Okay? This is just simple mathematics. If you know a multivariate calculus, you can actually do it. So the idea is actually to go from, so this is the conservative form written in a quasi-linear form. So basically this form, U is a conservative variable, and this is A, right? Now this is the primitive form of Euler equations. W are primitive variables. They cannot be written in conservative form. But you can actually transform from primitive to conservative and vice versa through this matrix Q. Okay, and this Q matrix is nothing but another sort of a Jacobian matrix, right? And if you know form of U, which is somewhere here, the form of W, you can create a Jacobian transformation from one to other, which is nothing but this. So this is one thing, and you can, The other is the characteristic form. This is where we want to go to. Okay. The characteristic form or the diagonal form breaks down this 3 by 3 matrix equation into independent scalar equations. That's like a great simplification. We dealt with scalar equations and we solved them, Euler and advection equation. And so this is the path here. The same thing. So you are making a transformation from u, which is the conserved variables, to v, right? And ultimately, this is the equivalent of multiplying this equation, the characteristic variable equation, by some matrix, okay, and transforming this A matrix into a diagonal matrix lambda, okay, and this is a similarity transform. If you've done linear algebra, if you do this transformation, the physical content of these equations are the same. That's why it's called a similarity transform. So if you do a similarity transform to the characteristic form, you get something which looks like the advection equation, or so this lambda is not linear, it's non-linear. So this looks like the advection equation, but lambda is a function of v. It's actually a non-linear scalar equation. That's where we want to go. So if you have a point here, this concept of domain of dependence and range of influence. So if you are a point here, nothing here can affect you because information from here has not had time enough to propagate to this point. You can only be affected by things happening here. This domain of domain of dependence, and similarly, this point can only affect this dome with its range of this basics of content of hyperbolic equations. This is the Euler equation. If you do this exercise for Euler equations, this is what you get. So these are those three beautiful equations that I was mentioning to you about. So this is the first one, the second one, and the third one. And you see these are eigenvalues of A. This Jacobian matrix. So you're not supposed to understand this. You're supposed to go back and look at it and try to derive it. So this is the characteristic. So the characteristic values of the eigenvalues are u minus a, u and u plus a. These are the sound waves u plus minus a. You are moving with velocity u and you're launching sound waves. Those are the sound waves in the lab plane if the fluid is moving. And then this u is this other characteristic u describes something called a contact wave or a contact discontinuity. Right? If you do those transforms, matrix transforms, these are the equations that you will get. So along these characteristics, this quantity is 0. Along characteristics moving with u, this quantity is 0. This is equivalent to saying that the entropy is conserved along that characteristic. This one is integrable. That's why you get S equals constant. These are in general non-integrable. You only have differential forms of it. For a specific case, if entropy is constant, then these can be integrated out, and these are called Riemann invariants. Okay. So this is about Riemann problem. Actually, I'm running out of time. I'm not going to go in detail with it. This is anyway my second last slide. Dipanjan will be talking more about it. But let me say what we are talking about. So, as he said, this Varno approach is, you take the dependent variable and break it down into piecewise constant initial conditions. So this is a Riemann problem. And I said, I just sort of very briefly outlined how you convert this 3x3 matrix equation into 3 independent scalar equations. So that's sort of symbolically shown here. So you have this initial condition, only density is shown. You'll have a similar initial condition in velocity and pressure. This has 3 waves sitting in that discontinuity. And it breaks out into this short wave, this contact wave, and this wave fraction, this is wave fraction. Okay? And basically, you know the solution of the unknown u at this discontinuity. Once you know that, you know the flux that you want in the Gordon method. Okay? So this is sort of what we'll actually do later. So we've already talked about this a little bit about history. Actually, Gordon in 1965, came up with his method. He solved the Riemann problem analytically. For Euler equation, you can actually solve it analytically. Okay. Now, this is only a first-order accurate method, and piecewise constant does not get you a very high accuracy. But there were these people who suggested higher order sort of generalizations of this. And the interesting thing is, Godunov was a mathematician. Boris was a plasma physicist. Van Leer started as a graduate student in astrophysics. He was student of Van der Hulst, who was co-inventor of 21 centimeter hyperfine transition that we see. So basically, this is an extremely interdisciplinary area. Aerospace engineers, mechanical engineers, astrophysicists, mathematicians, everyone sort of work on these different aspects of these equations. And these are the references that I would sort of share with you. A lot of this is actually based on these books, Laney and Levine, and a little bit of Toro. Yeah, same thing in slightly different way. Okay, thank you.